Good morning. Today we will solve some numerical problems from the chapter Thermodynamics. I didn't get any doubts from you yet, but I have marked some problems which I feel are worth discussing. So let us go to the problems. If you have your textbook with you, you can take page number 46. Anyway, I will read out the question and write down the important points. So let me first consider the problem 1.22. Question number 22. The ratio of compression and expansion at every step of a Carnot engine is 1:2. So they have mentioned the ratio of compression and expansion is 1:2. 3 mole diatomic gas. So they have given that the number of moles is equal to 3. 3 mole diatomic gas is used as working substance. And for diatomic gas, gamma is equal to 1.4. And they have also given a PV diagram for the working of a Carnot engine. And the PV diagram, they have just mentioned the gas going from A to B, B to C, and C to D. A, the pressure and volume is P1, V1. And here the pressure and volume are P2, V2. And the pressure and volume are P3, V3, P4, V4, and the temperature here T1 they have given as equal to 30 degrees Celsius. And here they have given the temperature T2. They haven't given the temperature T2. They just mentioned that the temperature is T2. They didn't give the value. And these are the quantities given in the question. Now let's see what is the question. First question is calculate the amount of work done between the point A to B of the Carnot cycle. So when it go from A to B, what is the work done? Work done is equal to what as it go from A to B? That is question number A. And question number B is it possible to become the efficiency of the given engine more than 33%? Answer with mathematical reasoning. So is it possible? So delta is more than 33%. Is it possible? This is the question. So here we have the question. Why I selected this is that when they mention that the compression and expansion is in the ratio 1:2, it means that if the gas expand, its volume becomes double. And if the gas compress, its volume becomes half. That is the meaning of telling the compression and expansion are in the ratio 1:2. This is one point where you get confused. Now, what is the work done as the gas go from A to B? So A to B. And what is the expression for work done? We know that the work done, because this is a isothermal expansion. In an isothermal expansion or any case, the work done W is equal to PdV. That is pressure into change in volume, right? And here, as it go from A to B, the pressure is changing. Pressure is not constant. So you have to go from V1 to V2, which means you have to integrate from V1 to V2, PdV, but P is not a constant. So let us take the gas equation. While we derived in the chapter, we took for 1 mole of gas. Here the case is not 1 mole of gas, so we cannot directly use that equation, but we have to put the value of N as well. So let me use the ideal gas equation, which is PV is equal to nRT. T is a constant, R is a constant, N is given. So you can tell P in terms of volume using this equation. Pressure is equal to nRT divided by V. So before integrating, I'm substituting this value for pressure in this equation. So the work done is equal to integral V1 to V2 instead of P, nRT by V into dV. So nRT is a constant which goes out, nRT into dV by V is there, which will be integrated from V1 to V2. Now note the point 1 by V dV. Integral 1 by V dV is log V. Applied between the limits V2 and V1. So work done will be equal to nRT between the log V between the limits V1 and V2. So when we put the upper and lower limit, the final expression will be nRT times log V2 minus log V1. Now we have all the expressions we can substitute here, or we can also put here this as equal to nRT times log V2 by V1. So here this is equal to N, they have given us 3 mole, 3 times R is universal gas constant, which has the value 8.31. You have to remember that value. R is equal to 8.31 multiplied by T is the absolute temperature. They have given it as degrees Celsius. So you have to convert it to Kelvin. How can we convert degrees Celsius to Kelvin?
Plus 273.
Plus 273. So just plus 273, which will give you how much? T's, right? So T1, let me just write here, T1 is equal to 273 plus 30, which is equal to 3 here, 7 plus 3 is 10, 1 balance. So 303 Kelvin. So you have to use that value here, 303 Kelvin multiplied by log of V2 by V1. See, V2 is after expansion. So from the ratio, we can understand that if the gas expands in this ratio, its volume becomes double. So if V1 is equal to, V2 will be equal to 2V. So I'm substituting instead of V2, 2V, and instead of V1, V. So log of 2V by V gets cancelled, so log 2. So you have here 3 times 8.31 times 303 times log 2. So when you can use your calculator to do that calculation, and finally you will get the expression number as 523.2, okay, not 5,235.89 joules, because work done, it's in joules. Is this clear to you how we calculated the work done?
Yes, teacher.
When you read the question, the point to understand is that the compression and expansion are in the ratio 1:2, means that when it compresses, its volume becomes half, and when it gets expanded, its volume becomes double. And also, when you calculate the work done for an isothermal expansion, remember pressure is changing. So when you integrate, you cannot take P as a constant outside. You have to use this expression and not use the derived equation which we studied when we learned theory, because that was for 1 mole of gas. Here they have given it for 3 mole. So you have to follow the procedure and get the answer. Is this clear to you? If it is clear, let us go to the next step, that is question B, whether the efficiency will be more than 33%. So for that, we have to find the efficiency. So to find the efficiency, we will have to know the temperatures at both stages. So here T1 is given, T2 is not given. So how to find T2? That is the issue. How we will find T2? Here we know that this is adiabatic expansion. B to C, it is adiabatic expansion, and this is where the temperature goes from T1 to T2, right? So here we can use the concept of adiabatic expansion. And what is the relation between temperature and volume for adiabatic expansion? Do you remember that? What is the expression for connecting temperature and volume for an adiabatic expansion, for any adiabatic change? For question B, we know that efficiency is equal to 1 minus T2 by T1 into 100 if you want it in percentage, so much percentage. We know that T1 is equal to how much? 303 Kelvin. But we don't know T2. So in order to find T2, let us consider this adiabatic expansion. For adiabatic expansion, we know that T V raised to gamma minus 1 is a constant. Right? You know this expression, T V raised to gamma minus 1 is a constant. So here to find T2, we will take the idea T1, V1 gamma minus 1 is equal to T2, V2 raised to gamma minus 1. So here we know the relation between V1 and V2. If V1 is V, V2 will be 2. So in order to find T2, I can write T2 is equal to, if I take this to the denominator, it will be T1, V1 by V2, both are raised to gamma minus 1. Both raised to gamma minus 1. And instead of V1 by V2, I can use this. Instead of V1, I am going to put V. Instead of V2, I am going to put 2V. So this is equal to T1 times V divided by 2V raised to gamma minus 1. Gamma is given. What is that? 1.4. So 1.4 minus 1 is, I'm going to put gamma also, 1.4 minus 1, which will be 0.4, right? So this is equal to T1 is 303. 303 times V gets cancelled. So what remains is 1 by 2. 1 by 2 is 0.5 raised to 0.4. So you have here the expression. You can again use the calculator to find that value, and you will get T2 as equal to 229.63 Kelvin. 229.63 Kelvin. Is it clear how we found T2? Is it clear till this?
Yeah, teacher.
Yes,
Oh.
teacher.
So once we have found T2, you can put the value of T2 in this expression to find the efficiency. So therefore efficiency eta is equal to 1 minus T2 is 229.63 divided by 303 and into 100. So that much percentage. Now, if you calculate that value, you will get it as equal to 24.21 percentage. So the efficiency of this heat engine can go only up to 24.21 percentage, which is below 33 percentage. So the answer is no. It is not possible to function this Carnot engine above and with the efficiency more than 33 percentage, because the maximum efficiency it can have is 24.21 percentage. Is this clear how we can solve this question?
Teacher,
Yes.
in some of the questions, they say that how can we make a normal Carnot engine like 75% efficiency?
Yeah.
So in that math, they decrease the sink temperature or increase the that one temperature. So in this case,
Yes.
we shouldn't. We will
Yes,
not do
yes,
that, right?
yes, you have got the correct point. They have told we can increase the efficiency of a Carnot engine either by increasing the temperature of the source or by decreasing the temperature of the sink. But here they have given the condition that the volume will only double during the process. So if the volume is doubling, what will be the temperature of the sink? That is what we have calculated. So under this condition that the volume will just double, we have calculated the zinc temperature. So this will be the temperature under which this machine is working now. We cannot do anything with the temperature. If the volume is just doubling, this will be the temperature. Now, if you want a lower temperature for the zinc, the volume should go some 4 times, 5 times, 6 times. But that's not the condition here. The condition given us, volume is just doubling. So that's the only possible value for temperature. Is that clear, Zaman?
Yes, got it.
Okay. So if they don't give this condition and ask you how you can make the efficiency of a temperature a particular value, you can put that value for the efficiency and find the temperature value and tell that if you keep the zinc at this temperature, then this will be the efficiency. If they haven't given this condition. Okay, so under this condition, the efficiency cannot be above 33%. So let me go to the next question. Now I have chosen the question 1.14. Okay, question number 1.14 in page number 42. So let me read out the question. Oh, before that, 1.19. 1.19 is also important. In page number 43, I will read out the question. What will be the change in entropy to convert 5 kilogram ice at 0 degrees Celsius to water at 100 degrees Celsius? Specific latent heat of fusion of ice is 336,000 joule per Kelvin, kilogram. Specific heat of water is 4,200 joule per kilogram per Kelvin. So let me write down what's given in the question. What will be the change in entropy? So they have to find, they want us to find the change in entropy to convert 5 kilogram ice. So 5 kilogram ice at 0 degrees Celsius, to water at 100 degrees Celsius. Water at 100 degrees Celsius. So what is the change in entropy as the ice goes to water and becomes at this temperature? Then they have given specific latent heat of fusion, LF. LF is the specific latent heat of fusion, just 336,000 joule per kilogram. And specific heat of water is equal to 4200 joule per kilogram per Kelvin. So this is the given condition. Now here we know that the entropy is defined as the amount of heat absorbed or rejected by the system divided by its absolute temperature, right? So entropy delta S is equal to delta Q divided by temperature. Now here, when we look at this case, 5 kilogram ice at 0 degrees Celsius. There are two changes taking place here. First, the ice will melt to water. Now, when ice melt to water, the amount of energy given is used to break the bonds, because ice is in solid form. It have to get converted to the liquid form. So first, the bonds between the molecules should be broken down when the ice, which is in solid state, go to water at 0 degrees Celsius. So there are two changes taking place. One is ice at 0 degrees Celsius going to water at 0 degrees Celsius. This is one change. And during this change, there is no change in temperature. All the energy given will be used up to break the bonds and change the state from solid to liquid. And the amount of heat energy required for 1 kilogram ice at 0 degrees Celsius to convert to 1 kilogram water at 0 degrees Celsius is called the latent heat of fusion. So it's for 1 kilogram. Okay, so you have to know this. So let me consider this stage as delta S1 is equal to delta Q1 by T1. Here, delta Q1 will be equal to the amount of heat given to 5 kilogram of ice at 0 degrees Celsius to convert to water, 5 kilogram of water at 0 degrees Celsius. So for 1 kilogram, the amount is latent heat of fusion. So for 5 kilogram, it will be 5 times the latent heat of fusion. Is it clear? Is this explanation clear to you? For
Yeah,
one,
teacher.
yeah, for 1 kilogram, it is latent heat of fusion. So for 5 kilogram, it will be 5 times the latent heat of fusion. So I can take this as equal to 5 times 33600. Okay, and the temperature is 0 degrees Celsius. So T1 is equal to, in degrees Celsius, this should be in Kelvin. So it will be 0 plus 273, which is equal to 273 Kelvin. So substituting these values, I will get, in the first case, when ice at 0 degree goes to water at 0 degree, delta S1, the change in entropy, will be equal to 5 times 33600. I think there are 3 zeros. Okay. 3 zeros divided by 273. And you can use your calculator. The value they got here is, the value they got for delta S1, it is equal to 6153.85 joule per Kelvin. Joule per Kelvin. So this is the change in entropy in the first case. Now, second case is, now you got water at 0 degrees Celsius. So water at 0 degrees Celsius going to water at 100 degrees Celsius. So water at 0 degrees Celsius going to water at 100 degrees Celsius, which means here there is a change in temperature. And we have already learned for 1 mole of gas, what is the change in entropy when there is a change in temperature. And the equation we derived was for I think it was for 1 mole of gas or 1 kilogram of gas. So let us find the expression for the total. So the change in entropy for the second case, delta S2 is equal to delta Q2 divided by T2. And here the temperature is changing. So what I have to do, instead of delta Q2, I have to write in terms of temperature, right? So we know that the specific heat capacity is defined as the amount of heat required to rise the temperature of 1 kilogram. So mass, 1 kilogram of a substance through 1 Kelvin. So change in temperature. So S is equal to dq or delta Q divided by mdt. So here I can write dq or delta Q, or let me write to avoid confusion. Delta Q is equal to Sm into dt. So instead of delta Q2, I'm going to substitute this value. So this is equal to, oh, it's not one fixed. So I'm just writing like this. So delta Q2 is equal to Sm dt. So Sm dt by T, and the total when water goes from this degree Celsius to this degree Celsius, delta S2 is equal to integrating it from temperature 1 to temperature 2. Temperature 1 is 0 degrees Celsius, temperature 2 is 100 degrees Celsius. So we have to integrate here. S, specific heat capacity, which is a constant. M, mass of the substance, which is a constant, 5 kilogram. So S and M I can take outside, and again log 1 by T dt. Sorry, integral 1 by T dt. So it will be log T within the limits T1 and T2. So this will be equal to Sm log T2 minus log T1. So now you can substitute the values. This is equal to S is what is given, right? 4200 times mass is 5 kilogram times 5 into logarithm of T2. T2 means 100. 100 plus 273 will give you 373. So log of 373 minus log T1 is 0 degrees Celsius. 0 plus 273 is 273 minus log 273. So you can calculate and you will get the value as S2, you will get the value finally. You can use your calculator. It's given here as 6,554.24. So 6,554.24 joule per Kelvin. So for the first case, this is the change in entropy, and for the second case, this is the change in entropy. So to get the total entropy, you have to add these two quantities. Is it clear to you? Is that clear to you?
Yeah, teacher.
Okay. So just to show that delta S is equal to delta S1 plus delta S2, I am rubbing a part of this, and then I will get delta S is equal to delta S1 plus delta S2. So this is equal to 6153.85 plus 6554.24. So this is equal to the total entropy. They got it as 12708.09 joule per Kelvin. So that is how we will find the total change in entropy when 5 kilogram of ice at 0 degrees Celsius goes to water at 5 kilogram of water at 100 degrees Celsius. So I hope this problem is clear to you now. Is it clear?
Yeah, teacher.
Okay. Now let's go to another question given in page number 42. So here I am considering question number 1.14. The question reads, the efficiency of a Carnot engine is 60% when the since temperature is 37 degrees Celsius. What is the change in temperature of source to make its efficiency 80%? Like the doubt Zaman asked, that we can change the temperature of the source or sink in order to change the efficiency. So here first case they have given that T1 efficiency of the Carnot engine is equal to 60%, and when the sink temperature is equal to temperature of the sink, usually we take it as T2 is equal to 37 degrees Celsius. Now what is the change in temperature? So let us take this case as eta and T2. Now what should be the change in temperature if the efficiency is to be made 80%? So the second case, we want an efficiency 80%. What should be the temperature of the source? T1. So the second case, when the efficiency is 80%, I'm putting that with a prime. So what is T1 prime? This is the question. So you have the efficiency 60% and the temperature of the sink as 37 degrees Celsius. So first of all, let us find the T1. So let us find T1 is equal to what? Then we can use here. What should be T2, right? Is that the good way? Did they ask anything like that? They just wanted to know what should be the efficiency, right? What is the change in temperature? Oh, what is the change in temperature? So they want to find what is change in temperature. So we know that to increase the temperature efficiency, the temperature of the source should be increased. So T1 prime minus T1 is equal to what? The change in temperature is what? This is the question. So we need to find T1 prime and we need to find T1 because this is the question. What is the change in temperature of the source? So let us first find T1. For that we will use the equation for efficiency. Eta is equal to 1 minus T2 by T1 into 100. So this is the expression. So 60 is equal to 1 minus T2 is given 37 degrees Celsius, which is equal to 37 plus 273, which is equal to 003, 300 Kelvin, minus 300 divided by T1 into 100. So into 100, if I take here, it will become 0.6.
Teacher,
Yes.
T2 will be 310 Kelvin.
273 plus 37, right? Yeah, right. Yeah, right. It's 10. 10, I forgot to take the one carry here. Okay, thank you, Jim. So it will be 310 Kelvin. So this is the expression. So when I take 100 here, it will become 0.6. So 0.6 is equal to T1. I'm taking this up. So T1 by T2, T1 by T1, I'm going to write this. So minus 110 divided by T1. So 0.6 T1 is equal to T1 minus 310. And therefore, when I take this to the side, so 310 is equal to T1 minus 0.6 T1. So this is 0.1 T1 minus 0.6 is 0.4. So 0.4 T1 is equal to 310, or T1 is equal to 310 divided by 0.4. What is that? 310 divided by 0.4 will be T1, which is equal to 75 Kelvin. 75 Kelvin. So we got T1. Now we have to find T1 prime. Here we have the efficiency, second efficiency, but they are not telling that they will change the temperature of the sink. So we will keep, in second case, the temperature of the sink same. So we have eta prime is equal to 1 minus T2 prime by T1 prime. And T2 prime we will keep same as T2 because we are not going to change the sign. So AT is equal to 1 minus T2 prime is again 310 Kelvin divided by T1 prime. So again into 100 into 100. So again 0.8 is equal to T1 prime minus 310 divided by T1 prime. Or if I take to other side and subtract, then I will get 110 is equal to T1 prime minus 0.8 T1 prime, which is equal to 0.2 T1 prime is 310. So T1 prime is equal to 310 divided by 0.2, which is equal to T2 is equal to, T1 prime is 1550 Kelvin. So we can find T1 prime minus T1, which is equal to 1550 minus 775. This is equal to, you can use your calculator, so no issue. It will be 775 Kelvin. Oh, which means the change in the source temperature should be 775 Kelvin. So we further increase the temperature of the source through 775 Kelvin. You can increase the efficiency to 80%. Is it clear? Is this clear to you?
Yes, teacher.
Okay, I think it's time now. Next period, we will have the test, right?
Yeah, teacher.